Three.
Welcome back, everyone. It's been a long time since we recorded our last session. We are back with machine learning and data science discussions. We are Petroleum from scratch. Today with me is Jayesh Chahar. I guess almost everyone knows him by now. I have with me Mr. Navdeep Dhaka, who is also one of our prime talents when it comes to mathematics and machine learning in oil and gas. So today we will be looking at a very important topic, which normally tends to be mathematically ignored by a lot of people before they start with linear regression. They just go ahead with, they get a data, they perform linear regression, they make predictions, they're happy with this error, or mean squared error and stuff, but they don't really dive deep into why a model is failing, why linear regression is not performing well, or they don't even consider whether linear regression should be the model in the first place. So today we will be looking at a very important conceptual discussion, which is like the heart before you start thinking about linear regression as the algorithm for your data set. We'll be looking at assumptions of linear regression that basically will, at the end of this video, teach you whether or not a particular data set is a candidate for linear regression as its algorithm. So Jayesh will be speaking a lot today. He has been using this concept a lot in his projects. So I'll be joining him wherever I would need to. Let's get started, Jayesh. Thanks for being with us.
Hello. Hello, everyone. So yeah, we will start our discussion for the today, that is assumptions of linear regression. So if you remember from our last discussion, what is a linear regression? A linear regression is basically nothing. We are just fitting a linear model between the given data points. We have our dependent variable, that is y, and we have our independent variables. Maybe it can be x, or it can be x1, x2, x3, and many more things. So we are going to build a model that will give us a linear relationship between this y and these independent variables x. That is basically our linear regression. So about linear regression, we already discussed. We also have a coding project regarding linear regression. So in this video, we will discuss what are the basic assumptions, what are the assumptions of a linear regression model, what things need to be fulfilled for a linear regression model to give us a good result. So these are the five main assumptions that need to be fulfilled for a linear regression. First one is linearity, then homoscedasticity, and then independence, normality, and no autocorrelation. We will see each of them in our coming slides. What are these things? So starting with the linearity. As the name suggests, linear regression means a linear relationship between your dependent and independent variable. So linearity assumption just said that there should be a linear relationship already present in our data. Only in that case we can fit a linear regression line or plane or anything if we have a higher dimensional data. Now, what is this linear regression? Linear relationship means in terms of mathematics. So basically, linear relationship means that if we change the value of y, what will be the change of value of y if we change the value of x? So it means that if we change our value of x by 1 unit, the change in value of y will remain constant regardless of any value of x, whether x is having some large values. For example, if I'm changing my x value from 1000 to 1001, or either I am changing my x value from 2 to 3, the change in the value of y will be constant, or you can say delta y will be equal to constant. So if we see our mathematics term, let us say that we have a feature x and we have a label y, and we have fitted a straight line between them, and my equation of line is y equal to mx plus c. So if I'm going to increase my x by 1 unit, my new y dash will be equal to mx plus 1 plus c, and the change in value of y dash minus y will be equal to m. That is nothing but a constant value. So this means this is the thing that is behind the linear relationship between y and x. Basically, change in value of y due to unit change in x will always remain constant. That is our linear relationship. So for fitting a linear model to a non-linear data set, sometimes what happens that we have a data set that is having some non-linear relationship with our y value or with our target value. For example, if I have a data of say a parabolic data of parabola y equal to x square. So my values of x are present for y and x present are different. For example, for x equal to 2, my y value will be 4, and for x equal to 3, my y value will be 9. So in those cases, for fitting a linear regression, we just need to use our higher polynomial terms. So in place of x, we will use our x square in our linear regression model, so that non-linearity can be tackled. Non-linearity problem can be tackled by using higher polynomial terms in our linear regression. That is also known as polynomial regression. In polynomial regression, we just do these things, that we introduce our higher dimensional terms to our linear regression model. So basically, we are fitting a linear regression model only, but my features will change from x to x square or x cube or under root of x or anything like that. Or sometimes also there is like not only just higher order polynomial terms, there are like a relationship between y and x is in terms of logarithmic relationship or exponential relationship. So all these things need to be done by us in our data and exploratory data analysis part, so that we can know how what is the relationship between y and x. I think Anshul Jha is entering the room. Yeah. So that is all linearity. Here in the graphs, you can also see that the upper plot is showing a linear regression between my y and x. Not perfectly linear, but it is a kind of linear. But in my lower plot, you can see that relationship between my y and x is not linear. It is kind of non-linear. It is kind of a quadratic relationship. So in this thing, we need to do the thing that I just mentioned. Instead of using x, we can use x square or higher order terms of my dependent variable, independent variable. So this is the linearity assumption. Now our next assumption for performing great in a linear regression model is homoscedasticity. So what is the homoscedasticity? It basically means that my error term must have a constant variance around my independent variables. So what
So
does this?
Jesh, let's do it this way. Like, you elaborately discuss on the topic, and then I finally conclude by giving an example. So basically, we talk about linearity first up. So, for example, one of our features, suppose it is sin x, right? Sinusoidal x. So in that case, the data is not, linear, right? So it's one. So for example, you gave me an example, x squared. If you want to fit it in a linear regression model rather than just x, you can use x squared as the feature, and then that becomes a linear model, right? But what if it was more complex, right? Where it was sin x, right? Basically, it was data where if you apply the sinusoidal of the data, then it becomes a linear function of y, right? For example, y equals to a sin x, y equals to 2 sin x. So y is in this case not proportional to x. It's not linearly related with x. But if you apply sinusoidal to your x, then it becomes linearly related with y, right? So user can also spend time in the early days on this data set. They can do hidden trial. They can do logarithm on x and compare it with y, plot it with y. They can do various combinations. Given you can do that, of course, a huge data set would not allow it, but pick up any random data set, apply such operations, do sin x, tan x, and figure out if in case you attain some sort of linearity, go ahead with the linear regression model with y and sin x, right? And then that would give you an understanding whether this assumption of linearity you have understood well or not. Because if you go with x and y, the model will fail. If you go with sin x and y, your model will succeed. So why does that succeed? Linearity assumption. Thanks, Chase. Let's go forward and
Yeah,
talk about the
exactly.
next one.
Exactly like this. So yeah, you have more data for y and x. Let us say, as Devanshu said, y is kind of function of sin x. So we just applied the sinusoidal function on our x independent variable, and let us say this new function, new terms that are coming. Let us name them t, and t is nothing but sin x. And now we are going to fit our linear model between y and t, and it will go out to a linear model. As you remember, in one of our project, we are getting some relationship between API, gravity, and viscosity. Devanshu, we spend a lot. You spend a lot of time for getting that relationship, so that we can define a
Yep.
great relationship between them. So
Exactly.
yeah, this was about linearity. Our next assumption is homoscedasticity. Homoscedasticity. So basically, what this means that our error terms must have a constant variance around our independent variable. So what does this mean? Basically, you will understand this by these graphs only. So basically, what does this mean? That my error term, or you can say my y predicted minus y actual, that need to be constant. That need to be constantly varied about each and every point. Distribution need to be constant. It doesn't be like that, okay, for small values of x I am getting a huge errors, and for large values of x I am getting a small error. It doesn't be like that only. The spread need to be constant for all values of your independent variable. So for example, here you can see I have plotted my independent variable versus, I have plotted my predicted value versus residual values plots for three different cases. Now the upper one, the first case shows that for smaller values of ypred and higher values of ypred, my error value or my loss values is very large. It is kind of spread. But for middle values, it is not spread. It is narrowed down. So this is a case of heteroscedasticity. Means my model is performing great for the medium values of my y predicted, but it is performing worse for the smaller values of ypred and higher values of ypred. In a similar way, for the last figure, you can see that as the value of ypred is increasing, my error variance in error is decreasing. So basically, for smaller values of my y predicted, the error chances of error, or you can say that loss term is very large. But as the my y predicted is increasing, the loss value has been decreasing. So it is also not a good case for performing your linear regression. Our best case for performing a linear regression is this middle one, in which we are having a uniform spread across the line, uniform spread across my all predicted values of y. It is not kind of biased toward the higher values of y or towards the lesser values of y. So this is homoscedasticity. It need to be there for a linear regression to perform well. There should be no clear pattern in distribution, and if there is a specific pattern, the data is heteroscedastic, as you can see from the first and third plots, that there is a pattern. It is a bowtine pattern. First, the variance is decreasing, then it is increasing, and for the lower one, the variance is decreasing with increase of value of ypred. But in the middle one, there is no pattern. So that is my homoscedasticity data.
So if I'm understanding it correctly, what homoscedasticity means is your model should not be partial towards predicting any magnitude of y. So suppose your y as a population, y varies from 0 to 100. So if it's giving an error in predictions, it should give a constant variance across this range. If it's ideally performing very well, it should perform very well across 0 to 100. But if it is failing somewhere, it is doing well at the other parts of this range, then this model has not understood the data totally. Because for small values of x, small predictions of y, it is doing well maybe, but for large values, it's not able to do well. Or in the other case, for some range of x, it is able to do well, but for other ranges of X, it's not able to do well. So great point. I did not personally know that, but I think it's very important. I have seen projects where this thing now being put into words explains why that model was failing. But yep, I think good
Yeah.
discussion on this part.
Yeah, one more thing about here is, for example, if we have outliers present in our data and we haven't removed them, so sometimes what happens that our model parameters are adjusted in that way that it is kind of biased toward outliers. So if we take example of this third figure, let us assume that it is having uniform variance till this point, and the point above these are outliers. So variance of errors is kind of decreasing. So basically our parameters of our linear regression model are kind of biased towards outliers. That's why it is giving less errors towards the my right hand side. So yeah, one way to deal with the homoscedasticity is to deal with outliers and all those things. So
Right.
yeah, anything you want to add more?
Nope. Good enough.
So yeah, our next assumption is independence. But what does independence means? That each of the features present in my data set need to be independent of each other. There will be a little or no, not at all collinearity between features. Now, what is collinearity? So in layman terms, collinearity means nothing that my one feature is related with the other feature. If I am changing the value of one feature, let us say we have features x1 and x2. If I am changing the value of x1, my x2 is also changing. For example, if I'm increasing my value of x1 and my x2 value is also increasing, so that you can see it is that you can say that it is a positive correlation, meaning the increasing of one value kind of directly related to each other. And if my value of x2 is decreasing with increase in x1, that is my negatively correlated, or you can say inversely proportional. So these things are correlation, or you can also say collinearity. Actually both are different terms, but for simplicity purpose we are saying that both are kind of equal right here. In our next discussion we will discuss the difference between collinearity and correlation. So what does this independence assumption say? That none of the features are dependent on each other, or none of the features are correlated to each other. If there is a correlation, that need to be very, very less. So why does this assumption comes into first place? Why we need to remove highly correlated features? We will see that in mathematically what is happening. So when we perform a linear regression, what happens that we are kind of fitting, again, let us take example for y and x. We are kind of fitting a y equal to mx plus c type of line. And from data, we are kind of calculating the values of c and m, because we have values of y and m, y and x. So this was for my two-dimensional data. What happens if I am having a multivariate linear regression? I am having x1, x2, x3 number of large number of features. So in that, my linear regression equation will look like this: y equal to m1 x1 plus m2 x2 plus m3 x3 plus c. So ideally, what need to happen that my all other values x2, x2, x3, x4 all are constant, and I am changing my value of x1, and I am kind of observing the how my y is changing with x1. So according to the depending on the that change in my y value with the change in x1 value, my m1 value is estimated. Ideally this needs to be happen. But if my x1, x2, x3 all these features are correlated with each other, what will happen that when I am going to change my x1 values, the x2 and x3 values are also going to change. So in that case, the estimating the values for m1, m2 or m3 would become very complex. So because of this, we need to deal with these highly correlated or highly collineated features. Now, the stronger the correlation between x1 and x2, all these values are, the more difficult it is to change one feature without changing the other. And with changing the other features, my whole idea behind estimating the M1 and M2 is kind of stuck somewhere. It becomes very difficult for the model to estimate relationship between my feature Y value and my target value independently. So that's why we need to deal with this multi-collinearity. So what we can do here, that either we can remove the highly correlated features. For example, I am having features x1, x2, and x3, and I know that x2 and x3 are highly correlated. So in that case, either I can choose only x2 or I can choose only x3, depending on my used case, or depending on my scenario. What is the total, what is my problem statement, depending on that. Or you can also kind of use principal component analysis and kind of club the features together. So these two are the things that we can do in case of highly correlated features. How you can know about a correlation between the features? Either you can use the correlation matrices like Pearson correlation and Spearman rank matrix, or you can use pair plots and visualize different scatter plots between different features and kind of see the relationship if there is some present. So yeah, this is the independence. You want to add something? Okay.
No, I think this is pretty intuitive anyway. People should know that no two features should be interdependent. For example, if you have x as a feature and 1 minus x as another feature, then it does not make sense to have both of them in the part of the same data set, because what x is conveying, 1 minus x is also conveying, right? X is negatively correlated, I guess, 100% with 1 minus x. So this is a pure example of where you should make sure that you don't supply redundant information. So we make sure we check for independence so that we don't supply any redundant or unnecessary information which has already been presented in some other feature. So yeah, Jayesh, you can carry.
So yeah. So our next assumption is normality. Now, what does this says? This says that our residuals should be normally distributed, as well as our feature values need to be normally distributed. What happens that our machine learning algorithm performs well on the normally distributed data. That's why our data need to be normally distributed. Apart from that, our residuals also need to be normally distributed. Now, there is one catch here. If my sample size is very, very high, this normality assumption that my residual should be normally distributed is kind of not necessary. Why? Because of a great thing known as central limit theorem. Now, this central limit theorem, we will cover it in our statistics playlist in near future. So basically what happens that if our sample size increases, we are kind of taking repeated sampling from our population. And for large sample sizes, the distribution of ordinary least square error of regression coefficient follows a normal distribution automatically. So that's why this normality assumption of residual is not needed when the sample size is very, very high. It is only in the scenario when my sample size is low, we are dealing with 1,000 or 2,000 data points. In that thing, we need to take care that our residuals are normally distributed. Now, what we should do if our data is not normally distributed, you can use standard scalar for distributing the data into for changing the data, scaling the data into a normal standard normal distribution, and use that for your training of the model. Yeah. You want to add it? Or go ahead. Okay. Now, our last assumption is no autocorrelation. Now, this assumption is very important when we are dealing with some time series data, for example, stock prices forecasting, or for example, rain prediction across the year, or rain forecasting across the years. So in those things, this need to be very important. On other data set, autocorrelation doesn't play any role. So basically, what is autocorrelation? Autocorrelation says that my one value of my y at some time t is not dependent on a value of my y in some previous time t minus 1. So your value of y, or you can say your value of stock today, should not be dependent on my value of stock that yesterday or the day before yesterday. So this is correlation. This is autocorrelation. We are kind of getting the correlation with itself only, but at different time step. For example, if you are having a temperature data, you know that after 6 months your season is going to change from summer to winter, and after 1 year again winter is coming. If today we are having a winter, after 1 year again winter is coming. So our temperature is going to have some autocorrelation with the temperature of 1 year ago. So what does this assumption says? That linear regression analysis required that there is little or no autocorrelation in the data. Now, if the the presence of correlation in error terms drastically reduces the model accuracy. So basically what happens that if the autocorrelation is present, the error that we are calculating is kind of underestimated than the true standard error that is present. So basically there need to be no autocorrelation present whenever we are dealing with the time series data and we are going to apply linear regression. So these are the assumptions for linear regression for performing good. You want to add something?
Yeah, I mean, autocorrelation is more important of a concept when it comes to time series forecasting. In that case, it becomes our friend. So we want to find out or quantify the autocorrelation magnitude. Auto means self. Correlation means, of course, you know what correlation means. So autocorrelation is a measure of how much a series is related to itself. So when it's a time series, is the sales of today, are they related to the sales of yesterday? Are sales of tomorrow related to the sales of day before yesterday? So as you keep on increasing the time lag, the relationship keeps on fading away. So that's important in time series, but yeah, curious to see. I'll have to read more about impacts of autocorrelation and linear regression. But thanks for bringing it.
Yeah, you can use lag plots for visualizing in initial stages that there is some autocorrelation present or not. So if in certain feature there is autocorrelation present, just leave that feature in the final training of the model. So I think these are the assumptions for a linear regression model to perform well. In our upcoming video, I think we are going to start logistic regression or something like that. We will see. So thank you. I hope you guys like the video. Please subscribe to the channel. Have a good day. Bye bye. Thank you.